good morning to all of you and welcome back to a new semester. So, this particular course is titled Micro Nanoscale Energy Transport, and my name is Dr. Arvind Patamatta and I am a associate professor in the Department of Mechanical Engineering working in the area of micro nanoscale heat transfer. So, let me briefly introduce the course content that we will be talking about before we move on to the introduction part of this course. So, I have also made a time plan of how many lectures that I will be talking with each topic. So, we will have first 2 weeks we will be spending time on the introduction part. So, why do we take 2 weeks here? Because the introduction is not just a PowerPoint introduction that I will be showing in the next two or three classes. It will also involve some fundamentals which probably you need to, some fundamental terminology and fundamental understanding of some basics which you need to know before we go into the subject wise topics such as the quantum mechanics, for example. That is the next topic that we will be looking at. So, the introduction will be a little bit more elaborate here, and then this will be followed by some understanding of quantum mechanics, because if you are looking at nanoscale energy transport, essentially you have to look at the duality of matter. So, either it could be a wave nature or it could be a particle nature. So, to understand the wave nature, so you have to deal with the theory of wave equation, Schrodinger's wave equation, solving the Schrodinger's wave equation for some simple systems. So, following that, now from quantum mechanics we have to gradually move towards the statistical thermodynamics. Okay. Now, to do that we need to understand the system to which we apply the quantum mechanics. So, quantum mechanics can be applied to as simple as an infinite potential well, which is like the textbook problem that we will do, to something like understanding solid state physics. The statistical thermodynamics is basically the bridge or the interlink between the phenomena at nanoscale and the properties at the macro scale. Okay. So, properties such as heat capacity and internal energy have actually a nanoscale basis, and we can understand that through the quantum mechanics and looking at the energy states at the molecular level. But how do we directly link that to a macro scale property like temperature and heat capacity is done through the statistical thermodynamics. So, we are not interested now in looking at each and every energy state possessed by a molecule or whatever energy carrier, but finally you are looking at a statistical ensemble of these, and this is what is going to affect the properties of this system at the macro scale. But we will talk about the derivation of some of the important distribution functions, the equilibrium distribution functions, so which you are heard about this. So, the Fermi-Dirac distribution function, the Maxwell distribution function, the Boltzmann distribution, Bose-Einstein distribution function. So, these distribution functions are the most important fundamental distribution functions covering all the energy carriers. Okay. And from there we will go on to define the macro scale properties, okay, such as the internal energy, specific heat and so on. Now, then we will move on to continuum level, okay, but something at the scales of the microns to 1 millimeter or 2 millimeters, where you have some certain interesting phenomena happening, but they are all happening still at the continuum level. Okay. So, to study that again we have to start with convection. So, when you talk about nanoscales, there is nothing like convection at nanoscales, it is all pure conduction, because you are talking about each and every energy carrier and there is no bulk transport at the level scale of the energy carrier itself. Okay, it is just collisions and transport of energy. So, it is primarily diffusion, and therefore, when we talk about conduction it is at the nanoscales, but when we talk about convection it is at the micro scales. Okay. So, you have a bulk velocity and there is a motion of the fluid and so on, and but there is a certain interesting things associated with the surface forces that we will look at. So, that we classify this again whether we are looking at a single phase system or a multi phase system. So, the single phase, so following this we will also look at phase change. So, not only the single phase change here, now when I say phase change, it is also phase change due to evaporation or condensation or two phase flows. Okay. So, two phase flows could be a simple mixture of air and water, okay, and then you have different two phase patterns, and the pressure drop and these kind of things, pressure drop parameters are affected by the different flow regimes, okay, arising out of simply mixing air and water in a classical T junction, okay, and then you just look at all the flow patterns and study that. So, that is a simple two phase flow, but there can also be a state where you have purely evaporation and condensation. So, this is a classical phase change problem. So, how the phase change problem in micro and nano scale looks, okay, and how it is different from your macro scale phase change. And we will also briefly look at nano fluids, because on a, I mean, although they are nano fluids, so you do not have any subcontinuum transport processes happening there, they are still in the continuum scale, but there are some important mechanisms such as slip between the nanoparticles and the base fluid, which could be at the micro and nano scales, and also certain phenomena which is different from the conventional fluids. So, what is causing the anomalous change in the thermophysical properties of nanofluids, and therefore, how they are utilized for efficient heat transport, for example. So, they are now increasingly becoming efficient fluids for better heat transfer, both in the conduction and in the convection sense. And finally, we will look at the applications. So, I think this is basically the theme of the this is how the course content has been designed. So, we see that we are covering quite a bit, we are not just focusing only on convection or conduction, but we are covering as much as possible. The breadth of the subject is quite large, and therefore, we have to see how much attention to detail we pay under each topic. Okay, thank you.